Right. Our speaker today is Professor Wojtek Palubicki from Poland. His work has been in the intersection of AI and computer graphics and natural phenomena, especially related to forests. We've actually, I've seen his work. I saw his work in Nature some years ago, which is absolutely brilliant computer graphics simulation of forests, not just of a forest, but the evolution of a forest, and being used in, as I remember from that time, in movies and things like that. So Yihan recommended that we write to him and ask him to give a presentation in this series. And I'm really so happy that you agreed. And though we haven't met, I know we will have a wonderful talk from you. So thank you so much for accepting our invitation, and look forward to your talk. It's all yours.
All right, so thanks a lot for the introduction, Professor Keshaf. So talk today will be about forest fire simulation. And I will just try to quickly walk you through it, what it takes essentially to make a realistic or as realistic as possible looking forest fire. And a lot of simulation work goes into that. So forest fires, of course, are very dramatic events. So here a video from the 2019 California forest fires. It's usually very difficult to make observations like when this event appears. And here, of course, computer graphics now recently has gained a lot of traction because actually it allows us to generate synthetic observations that could be useful, for example, for the training of AI agents, robots, without actually relying on real data. So the work that I present here is targeted towards a computer graphics audience, but it actually draws upon works coming from different disciplines. So it's a very interdisciplinary research work. So there's a long-standing tradition in computer graphics and modeling the development and the growth of trees and plants. There's also in the computer graphics community a huge number of papers on how to model terrain, on how to model plant ecosystems, as well as simulating fire and combustion. But this work will also draw upon ideas, and we will try to even compare analytically against simulation models published in the ecology domain as well. So, please also you can interrupt me when there's something not quite clear if I go a little bit too quickly over it, though we just have 30 minutes here to go through that. So what in a nutshell I will try to present today is a simulation framework. A mathematical model can be used to simulate very realistic 3D wildfires, and the input to that algorithm will be essentially something which represents the plant, the spatial layout and the shape of a plant, and also how it reacts physically to for example, heat and other physical parameters. So we will represent this as a plant graph, and the other part of the input will be some discretized simulation domain, will be a 3D domain in which we'll compute the fluid dynamics which underlie the wildfire simulation presented today. And with that input, essentially one way of trying to describe this model will be that we will use it to simulate fire, to animate fire. And these in turn will feed into a model which describes the combustion, which is occurring in the plant, on the surface of the plant, and the pyrolysis process, which is essentially feeding the wildfire. And we will use the results of this combustion simulation to determine how our trees, how our vegetation structures should deform, how they should change under the influence of this fire and the combustion of it. All right, so the tree models that we will be using for the first simulation, which I briefly describe, are generated from a graph description. So you can see on the right side a model of that. So the way the trees are represented is essentially by a set of connected vertices by edges, and the vertices are data structures which hold information about the mass and certain biomechanical attributes of the tree. We then use a physical simulation which is based on Koszorot rod dynamics. So you can think of it a little bit as a simplified Newtonian motion framework, where you essentially don't rely as forces as the main driver of the displacement of objects, but rather on the positions of objects relative to each other. And this we then use to generate a 3D mesh, as you usually do in computer graphics, to generate these renderings from 3D scenes. And we will update this with computer graphics algorithms so that we can have a dynamic animation of the tree. For the fire simulation, we will use something which we call in computer graphics, or also in computational fluid dynamics, an Eulerian fluid solver. So this is a computationally very efficient fluid solver, not as detailed as what you would, for example, use to simulate the flight of a rocket, but something which allows us to simulate the effects of fluid phenomena in interactive times. We will simulate it as a temperature field which evolves in a gaseous fluid. We also will simulate other effects such as smoke using this type of description. So I will focus on here in this talk about on the combustion model itself. So this is one of the novel contributions that we had, like as part of a series of papers on this topic. And here we will look at what are the conditions for flame spread, how the material is decomposing under the influence of fire. And this is something which we'll call pyrolysis. And then the third point will be the heat and mass transfer between the atmosphere and the tree and the vegetation itself. So the most fundamental way or descriptive element that we use to express the structure and the biomechanical properties of vegetation is something which we call surface elements. And surface elements, you can think of it essentially as like a chunk, like this little cake chunk of a part of a tree, of a branch segment. Think of it maybe like as an internode, and inside that internode, we essentially just discretize this cake piece, and we then store certain physical quantities and geometric quantities that describe the evolution of this cake piece of a part of a tree over time. So these surface elements essentially then are arranged in this cylindrical manner around the branch, and they have a certain height h0 at the start of the simulation. So before the onset of combustion, before the onset of this process of pyrolysis, we'll have some kind of, let's say, like resting height of these surface elements. And as then pyrolysis onsets, then the height of the surface element decreases. So pyrolysis is a phenomenon which occurs in a relatively thin part of the volumetric branch portion. So it's usually just a few millimeters thick, and you can think of it as sort of like this surface where we have a lot of chemical reaction happening, which eats its way somehow into the branch. And as a result of pyrolysis, essentially wood is turned into charcoal, into char, as well as into gases, which then enable like all these chemical reactions, which we see in the end as fire or as flames. So we call this part of pyrolysis then also the pyrolyzing front, and we essentially model here, represent, describe the pyrolyzing front here essentially as sort of like these height changes of these surface elements. So this is not a three-dimensional combustion model, as you could also do, and in with wood technology departments, there are many people who generate very detailed simulations of volumetric combustion. but these are computationally very intensive and would not be very conducive to our goal of having an interactive framework where we can simulate the combustion of a whole tree and even maybe part of a forest. So mathematically, this parameter h of our surface elements is essentially given here by this equation, where m is the mass of a surface element at a given time point, h0 is its starting height, rho is the density of the wood, and a0 would be the surface area of the surface element, so like the top part of the surface element. So the only variable here over time is then the mass. So the height is essentially given, in this case, completely as a function of the mass of the surface element. We also compute the height of the char layer, and here we assume a linear relationship where we have some kind of coefficient kappa, which tells us essentially for different types of wood, how much char layer do we expect as the result of a difference between the starting height of a surface element and its current height of the element. So this linear relationship is something that is also assumed in the wood technology literature under certain conditions, in certain like temperature ranges. This is something that indeed has often been expressed in the literature as being able to approximately express with such a linear relationship. So we follow here the findings in these wood technology papers. So to using this height of the char layer, we then determine an insulation strength on it, which can impact the mass loss rate of the surface element. And here the insulation strengths essentially here function over the char layer height HC, and we assume that there is a minimal, a C min variable where our surface element would have the maximum insulation strength, and assume here this exponential relationship between the height, the thickness of this char layer, and its ability to insulate the wood from the fire. So here are the equation on the mass loss. So here the mass loss is proportional to the surface area of a surface element. So here we assume essentially that the pyrolyzing front occurs simply over a surface. So that's why this relationship in approximation can be given as proportional to simply the surface area. We assume that there is some kind of car insulation parameter, which is computed just as on the slide before, which tells us essentially it is derived from the thickness of the char layer. And then there's a reaction rate function, K, which is dependent on the temperature. So the shape of this reaction rate function, or an example shape, you see here sketched out on the right side of the slide, with the only caveat that essentially below a simple some kind of ignition temperature, we just zero this sigmoidal function. And then as the temperature here shown on the horizontal axis increases, so the reaction rate K increases as well, which means when the higher K is, the higher the surface area is, well, then here the higher the mass loss rate, and the lower the insulation coefficient C will be, the greater the insulation effect is on the tree. We also simulate the water content. So here the water content is essentially proportional to the temperature and some kind of evaporation rate coefficient. The more water is released by the branches, here we could visually then simulate here different effects of smoke. So we could assume that if there's more water released, that we have more water vapor in the air, which we can then visualize using our 3D simulation, like computational fluid dynamics framework, like in a different way. So this is now the core equations of our simulation. Here we define the changes of temperature over time. So here Ts is the temperature of a surface element. And here we assume that there's some kind of conduction happening of the temperature over a domain which is two-dimensional. So in essence, the surface elements which are neighboring to each other, they exchange heat with each other, and this is captured by this term. Then we assume that there is a cooling or a heating component as well. This is essentially coming from Newton's cooling or heating law, where we look at the difference between the ambient temperature and the current temperature of the surface element times some kind of scaling coefficient. And this tells us essentially like what is the conduction of heat between the air surrounding our surface element, exactly, the air surrounding our surface element.
Can I ask you a question?
Yes, please go ahead.
The previous slide, where you had the W parameter for the water loss,
Yes.
W. I mean, there's this W parameter is basically species specific, I assume. You know, for each tree species, you'll have a different parameter.
Yes, this would be like when expressed with your evaporation rate. So we could assume that this evaporation rate essentially would express some kind of species specific way of evaporating.
Asking is, you know, because let's say that you have a firefighting and somebody's adding water to the surface, you know.
Yes.
So how does that get expressed over here? Does that change then? I mean, because you don't seem to have an initial,
Yes.
you don't have a W or something like that.
Yes, yes. I mean, so in fact, in this model, it is not considered. We have actually a publication this year where we do consider a cooling effect of air, and I will show a model here, like in a little bit if we have time, hopefully, that actually takes into account also the cooling effect of rain as well. So, but in this very simple first model that I'm presenting, you're absolutely right. So there should be actually some cooling effect of the water that is not part of the tree itself, but this is not simulated in this framework here.
But just quickly, in the species here would be both W and omega, right? It'd be both of the W's, because the original water content also is species specific.
I suppose so, yeah.
It seems a whole bunch of
W and small W both, yeah.
Sorry, acoustically, I didn't fully hear sort of like
Oh,
what.
I'm sorry. I was just saying that other variables in this equation would also be species specific, like the original water content.
About variables, yeah. I mean, like, so if you mean like for here, for example, like are these also species dependent parameters? Yes. I mean, for example, like for the car insulation, we have like this C min parameter. So this would be something which is species dependent. This is something that actually we looked up in the wood technology literature, or essentially for different types of wood, like a different C min parameter is presented. So this is actually an equation we took directly from the literature, and there do exist actually also then comparisons to real observations that over some kind of range of conditions show that these C-min parameters are like a somewhat reasonable approximation of reality.
Thank you.
Yep. So where were we here? I think. So okay. So just as a recap, so this is the rate of change of a surface element temperature, right? So this is a two-dimensional domain, and this is now the rate of change of a temperature in the atmosphere in this fluid grid in which we embed our data structure which represents the plant. And here we again have sort of like this conduction, this diffusion term, although this spatial domain here is three-dimensional. We also have advection of the temperature field, and we again have this radiative cooling term. It looks very similar. The only difference is here, so this T amp is essentially the ambient temperature, so it's more like a macroscopic temperature of like the whole space in which we are simulating, you can think of. and it's here taken to the power of 4. Why to the power of 4? I mean, this is really something we took from a paper as well. This seems simply to be a better approximation to observational data. So this is a high-level model of heat transfer, where simply taking it to the power of 4 seems to account for certain other radiation processes which in this coarse model are not accounted for, but this can be ameliorated essentially by adding sort of like this exponent of 4 here to this cooling component of the equation. And we also make it dependent, of course, now on the temperature of our surface elements. So here, these Tm here is essentially the temperature that results from the mass loss of our surface elements. So this is the M in sort of like the definition of the height of our surface elements. The more mass is lost, which we know is a function over the reaction rate and the char insulation, as well as the surface area of the surface elements, well, the greater here the temperature will be, which will heat up essentially the air. And in this way, we are entering this bidirectional heat transfer feedback loop, where essentially the more mass is being combusted, the higher the temperature of the air is. But the higher the temperature of the air is, well, the higher the temperature of the surface, and we know that the reaction rate is a function over the temperature of the surface elements, which then results in higher mass loss, which of course again results in more heating. So and this is how from a small flame we can actually get to a fire that consumes like the whole tree in the end. All right, so let's look at some of the parameters which we now have defined through these equations. So here a mass loss rate coefficient. Now we are turning here some branches on fire on the left and the right C. So you can see it's an interactive simulation that we can compute. This is implemented on the graphics card. We can now reduce the mass loss rate, which will slow down essentially here all these processes. And this is then visibly seen as a reduced flames. Here another coefficient, the temperature diffusion coefficient. If we increase it, then the conduction of temperature between surface elements is increased and the fire propagates faster along the surface of the branches. If we increase now the moisture coefficient, well, we will see that here that more smoke is generated. And we have also here a visually different simulation with a higher moisture coefficient value. Then also, like, since we do have a physical model of the branches using Koszary-Rod physics, we can also compute here now like breaking threshold, at which point essentially a branch has lost so much mass that it structurally cannot support anymore its own weight. And at that point, we would simply disconnect it from the tree graph, and we can then simulate the falling and the collisions with the ground and other branches. So we also compared the simple model to some experimental data. So these are experiments which we did in Poznan. We went to the wood technology department and we looked actually in the combustion chamber, combusted wood samples. And we looked like just qualitatively what happens if we just change here the orientation, the spatial orientation of these wood samples, and can we simulate this also with our framework. And well, unsurprisingly, here using these standard solvers, it burns slower when it's in the skewed direction compared to when it is exactly parallel to the gravity vector. We also compared it quantitatively to mass loss rates measured for real wood samples. So here we have the experimental curve of the mass loss rate of a wood sample. So this mass loss increases exponentially to a certain time, at which point the mass loss then decreases again. This coincides, and this is very well known in the wood technology literature, to the formation of this char layer. So the char layer has this insulating effect, which then reduces the mass loss once it is formed. And here you can see the comparison to a naive model in red, which does not take into account the charring, which essentially does not use the insulation coefficient that we compute here from the height of the surface elements. It would not have this pronounced tipping point, but we can obtain this pronounced tipping point here with our model. Let's look now at some 3D animations of fire. So we could now, with such a model, try to burn and set the tree on fire from below or a little bit higher up. And this will now result in quite a different simulation, which is, of course, then more destructive from below, as the fire more quickly goes up than in other directions. So here, another example of how we can interact with the model. So here we again set some branches on fire. Then our fire simulation, our combustion model now goes over it. We can interact with the tree here and rip the tree apart. Can also generate other modes of interaction with our simulation. So here, for example, a wind field, which we impose on the fire. So here I've not shown you these equations. To be fair, this is something that we added here. So the wind can have at certain speeds a cooling effect, essentially has an effect on reducing the mass loss over time, which can then lead to the extinguishing of the fire. And we can, of course, now put more than one tree into our computational fluid simulation domain, which is a three-dimensional domain. And so here, if we take a few trees more and they're all in the simulation domain, then of course the temperature in the air then can mediate this the flame effect onto other trees. And so we can even simulate here the combustion of small growth of trees. But this is about the maximum that you can expect to simulate interactively with that FrameMat, at least like a couple of years ago. Maybe now you could put in a few more trees, but it would not allow you to simulate now a bigger chunk of a forest. And hence, to do that, essentially, like you could now formulate a model very similar to that at a higher scale of abstraction. The idea will be still very much the same, but instead of simulating the combustion at the level of surface elements, we would we would actually simulate it on the level of modules. So where we essentially say that a set of branches can be defined as a module, and that the whole shape of a tree is given essentially by these connected modules, which essentially mathematically would be a hierarchical graph, which then again we can use our computer graphics methods to generate a mesh out of and dynamically deform it over time as the combustion progresses. We again would then use a fluid simulation exactly very similar to the one for this more detailed simulation of combustion. So in essence here, I'll just go a little bit faster here. Tree presentation would be a truncated cone branch at the very lowest scale of abstraction. These then geometrically would represent segments of branches, which then together can define modules, and modules are essentially some kind of cone branches connected together. And with these modules, we would then compose the whole of the plan shape using some kind of biological principles of how these modules could be in, let's say, like a biologically plausible way connected to represent different types of tree species. But this I would have to omit for now. There's a lot of math underneath it of how this would be expressed. It's not that important now for the current presentation. And from this, we would again then generate the geometry of trees using our computer graphics methods. When it comes to the combustion itself, it's philosophically very exactly analogous to what we had before. So wood and heat is transformed to fuel and char. We again would have a differential equation describing the mass loss rate over time. And here this again would be proportional to the surface area, but this time of the modules, not the surface elements. There would be a char insulation for the modules, and there would be also a reaction rate function of a temperature of the modules instead of the temperature of the surface elements. And the reaction rate again would be a sigmoid function. Doesn't look like it now, but trust me, this is also very much a sigmoidal shape. This is just the computer graphics, a nerdy way of defining it, which lends itself very well to be computationally efficiently calculated on the graphics cards itself. And we would then also define this new function eta, which is a function of the wind velocity. And here essentially the higher the wind velocity over some kind of reference velocity, we would then have a cooling effect or like a slowdown effect essentially of the reaction rate computed on top of this sigmoidal function. When it comes to the heat transfer, we would also in very similar terms define it compared to this model expressed at the scale of surface elements. So here we would only, of course, now have a differential equation for the module temperature, which would again have this take into account the conduction of heat from nearby modules. We would have this heating and cooling term. And in addition, here we would now add rain cooling, assume that we want to now simulate a forest fire of a little bit bigger region, then this rain cooling effect could be very interesting to take into account. But maybe without delving here too much into the details, let me just continue, just so that we finish here on time. We looked and evaluated this model, which is based now on modules instead of surface elements, by looking at how the relative mass loss looks like as a function of the number of modules. And here, essentially, this lowest row represents a model where we express the plant shape with modules with only one module. And as we go here higher on this vertical axis, the same plant is represented by a higher number of modules. In this top row, we go to as high as 123 models. So this is composed of much more modules than the lowest one, but this is a very complex model. So here we essentially represent the topology and geometry of the tree with the truncated cones. And here we represent it with a higher number of modules, which were composed of simpler sets of connected truncated cones. And here we have graphs which describe the relative mass over time. So the green simulation represents now the most accurate representation in terms of number of modules. So here we would expect a more detailed representation or description of the combustion. And we can see here that maybe with one module, this diverges quite a bit. But if we have already something like 14 modules, we can actually really get a combustion, which is quite similar. And here, essentially using small number of modules seem to already give us a somewhat similar simulation compared to the more detailed description of the spatial layout of the fuel, which is contained in our plans. So here the same evaluation or validation of the model, where we look again at the number of modules, and here like over time what is happening. But here we're looking from the top down, the bird's eye view on a grove of trees, and see like how it changes over time as a forest fire progresses. And again, we're looking here at a number of relative mass loss rates on this graph on the right. All right, so this model is slightly more complex than the previous one. So this is some graphical visualization of the differential equations. which we're using here. So some of these I've shown you here in this presentation, such as the module combustion, for example, or the heat transfer, or the module temperature here. We also here have the Navier-Stokes equations for the wind field. We use a very simple weather model, essentially coming from the 1970s, which we extended slightly here, which is based on the Kessler model. And here we are tracking essentially the water in vapor form, in condensed form, and in rain form, and have here different conversion functions. And we then take this into account when we compute our heat transfer. So we can have a cooling effect here, for example, from rain, things which were not present in the simulation of a single tree. All right, but let's not go here into too much detail. In principle, this simulation expressed at the scale of modules, where some of the atmospheric processes are now a bit more detailed and we take more atmospheric processes into account compared to a different one, still allows us to simulate fire which interacts, or the combustion of vegetation which interact with each other via the atmosphere. So here a small plant can actually transfer heat through the air to a larger tree, which sets it then on fire. And this is how the forest fire would progress over time. Since we have here a very detailed spatial representation of the trees in this model, as well as of the forest fire itself, can now run different types of simulation experiments. So here with a natural barrier to the wildfire, in this case, we have a river which is thicker or thinner. In the thinner case, the heated air actually can start a forest fire on the other side of the river bank. In this case, it is so wide that actually it does not work. Can also look at the effect of slope on the progression of the forest fire. And here we, in this simulation experiment, we see that the propagation time ratio of the forest as a function of a slope of a terrain is what we would expect to happen in reality. So now we can generate some forests, we can develop some forests here, 2 different species, here in this darker color, some softwood, in this lighter color, we have a hardwood. Can now simulate here in a sped up way the progression of the forest fire. So the hardwood is more fire resistant to the fire. We can look at how the forest fire would progress in our simulation. Can also look at different vegetation cover, from very sparse to very dense. And here from the top down, how would affect then the progression of the forest fire over time using such a detailed geometric forest fire simulation framework. Of course, like since we're modeling the wind as well in our simulation, we can look also at the effects of wind on combustion. So this is now largely mathematically expressed by this eta function. So here with no wind, this would be how the simulation, and in this example, cast out. As we increase the wind speed, we get a different effect. Interestingly, like one would think that maybe, or at least like me naively, when at the beginning, if you have a faster wind, it should progress faster in that direction, which is indeed the case. But since here with a small wind velocity field imposed on the scene, the fire actually has more time to act over a given region. We have here the forest fire expanding a little bit to the right, which then gives us actually like a higher distraction, the distraction for this specific simulation. So here are a simulation of a forest as we are looking at it from the side. Blue is water vapor, which is here then evaporated by this process of combustion. This can then condense to a cloud, and the cloud can actually rain again. So this is something which our simulation framework allows for. These clouds are called with different names. One name is, for example, Flammagenitus clouds. And these Flammagenitus clouds actually are very interesting because they can interact and often do with the wildfire itself. So the rain is here not visualized in this particular simulation, but here actually it does start raining, and the rain can, for example, then extinguish the forest fire on the left side of a simulated area as we take this cooling effect of rain into account, which gives us here a very interesting simulation framework to explore very complex feedback loops. And of course, like these Flammagenitus clouds are actually quite important to simulate from purely visual perspective, because very often when we actually see a wildfire live, we're usually very far away, hopefully. And then what you see is actually not so much the fire itself, but it is actually mostly this Flammagenitus cloud or the smoke that is coming out of it. And these are then phenomena that we are able to simulate with our framework. We did also some quantitative comparisons in our most recent study, which has been published this year, and compared it to real observations here of controlled burn experiments. So take a look at that if you're interested in this. But I think I'm running out of time here. So let me conclude here this presentation, that what I showed you here was essentially two different types to simulate trees. One was a surface element based description of tree shape and its biomechanical and combustion relevant parameters, and another one which was module based, which allows us in comparison to the first model to now interactively simulate the wildfire of up to 100,000 trees. And there we take into account the processes of pyrolysis, mass loss, and heat transfer. We simulate the temperature field using a computational fluid dynamics. And this, in principle, altogether allows us for a fairly accurate representation of vegetation for our wildfire simulation. So this is something, again, comes mostly here from the computer graphics perspective, and there's now different trajectories in how we could extend it. So this year we also looked at more detailed simulations, and we tried to compare with historic wildfires, but that's something that maybe I can present like on another time. So we cannot put everything here into this presentation. So that would be it for me for today. Hope you enjoyed to learn a little bit about what we do in computer graphics, and overlapping maybe also with the interests here of what you guys are doing in ecology. Thank you very much.
Okay. Actually, we have plenty of time, so we have about 10 minutes more. So we do have time for a lot of questions. Any questions from the audience here? Yeah.
Thank you very much for your talk. My research is mainly about doing above ground biomass. So I'm quite interested in seeing, like, for the individual trees in this modeling approach, like in computer graphics, how realistic it is for every individual tree, like in terms of real tree allometry, or to improve this tree allometry of these digital trees based on some real world like laser scans.
Right. I mean, so that's nothing that what was important like in these simulations, but like we also do simulate the development and growth of trees and forests. And here we essentially have like different parameters which control like these developmental processes in trees. So we usually look at processes such as tropisms and other biological processes which are supposed to be important in the shape of a tree. So the allometry really is then the emergent result of the simulation of these biological processes in these simulations. So I think it would be easier if I would have a talk maybe given on that particular topic. Hopefully this makes somewhat sense what I'm saying. So here, like, I can just comment like one more thing. Like recently we actually did like a small project for Greenpeace South Korea, where we actually tried to look at the height development of white pine over time. And here we looked at observational data over time of how quickly that actually appears. And here we try to fit essentially our parameter values so that at the end of this emergent growth simulation, we see in different parameters such as carbon sequestration or biomass or volume of forest per hectare or things like this, that it conforms to this real data. Right, so this is research which we are just getting in. I think the report will be published soon, and it would be interesting to hear also like the opinions of ecologists. I am in touch with other professors from ecology, and like we discuss sort of like what is important here to capture in such simulations. But if you are interested to discuss as well, like how we could make these simulations more realistic and what other observational data we could include into validating these simulation models, like I would be very open to such discussions.
Yeah, sure. Yeah, thank you.
Thank you very much. Any other questions? Yeah, okay.
Yeah, thank you for the talk. That was really interesting. If I understand correctly, so you are modeling tree-to-tree ignition and reignition. Are you also looking at sort of initial ignition? So that might be from campfires or power lines or whatever. And if you are, does that have any implications for forecasting where future wildfires might occur?
Yeah, I mean, so we're not looking into that. That happens essentially on a different temporal scale. Of all, like here, these animations that I'm currently are running, actually they do have a soil model also in addition to what you've seen now in the second model that I presented here. And with such a soil model, of course, like then you have also like water content in different surface layers, and these are then the parameters which are used in like many predictive analytical models in wildfire prediction, which are used. So the temperature of a soil, for example, is something which is a very important parameter in determining like what is the probability of a wildfire occurring. So in principle, with this newer simulation, we do actually have data structure, and we track sort of like also the dynamics of these parameters over time, which would be very like important predictors for that. But these, like also the most recent simulation actually focuses on the dynamics as the wildfire is already like occurring, as it is in full motion. Like when it's occurring, it's just different physical processes which are at stake here. We are which are contributing to that, and while we are developing these data structures, which in principle are quite close to already potentially give us here some tool to conduct such simulation experiments as well. We have not looked at this in detail.
Thank you.
Yeah. Anybody online? You can just unmute yourself and ask the question.
So was it like a question to me, or like was it a question to the online audience?
The audience, sorry.
The audience, okay. Yeah.
Well, 10 people online. Looks like, but I had a couple of questions for you. One was, you emphasized in your work the role of the interactivity in the simulation as opposed to, something that you run.
Yes.
Why did you choose to train? Why is interactivity so important?
I mean, so there's a couple of arguments, but just to give you like my favorite one, to make it a super long answer, is essentially like here, what I found like most interesting in phenomena where there's not much analytical work like done, or like where we don't understand, let's say from a mechanistic, a causal point of view very well, and where we have a lot of agreement in the research community of how exactly like what drives wildfires. I find that an analytical tool which allows us to test and validate different hypotheses in real, like chronological time very quickly is something which is of immense value. in my opinion, right? So here we can now input essentially different type of hypotheses, especially like those which rely very much on, let's say, like a very detailed spatial representation are very interesting to test out with frameworks like this. And we can test out now a larger number of hypotheses in a shorter number of time. That would have a very detailed wildfire simulation, which takes a month to compute, and such frameworks do exist. Then, of course, I have to wait a long time before I see whether even qualitatively this hypothesis can be a good one to describe like the phenomena in reality. So that's why personally I find these interactive tools are a very good way to quickly traverse essentially a set of hypotheses and prune away hypotheses which seem just very implausible given the qualitative behavior that can be then witnessed in these simulation experiments.
Okay. I mean, I do believe you. It seems to me this sort of in silico type experimentation, and it relies on the underlying accuracy or reasonable accuracy of the models, so that the in silico experimentations are actually valid. I noticed you had some validation as well. So given how good this is, I was wondering whether this was used for training like firefighters or land managers or things like that.
Yeah, I mean, these are things which we are currently exploring. So just had one submission to an ecological journal where we compare to historical wildfires, where we compare to like the rothermal model of predicting the rate of spread of the fire line, for example, where we also more detail look at these controlled burn experiments. And we are essentially trying to calibrate the parameter values of our wildfire simulation in more detail to the actual physical ranges which we expect to occur in real scenarios, and then validate essentially like how well such models can simulate like these wildfires. And I think this would be the natural first step before we can talk about a tool for wildfires. So we would have to establish essentially over a range of comparisons with reality or analytical models which are known to predict rather well in certain scenarios. And I think if we come back with validations which would be satisfactory, then one could think really about like how to utilize such a very fast interactive method to then quickly augment the decision-making processes which underlie wildfire management services.
Great. Thank you very much for this. We are also at time, so thank you so much.
All right. Thank you very much for inviting me. I have very fond memories of Cambridge. I was also free as a postdoc in Cambridge at the Sainsbury Laboratory. So I love the city. It's beautiful. So I wish you a nice day today in Cambridge.
Yeah, and I hope we can see you in person. We'd love to talk to you when you're here.
I would love to come. If I will be in Cambridge and I'm every once in a while I'm there, I can drop you a message. Maybe we can then meet in real. It will be fantastic.
Please do that. Thank you very much. Thank you. Bye-bye.
Bye-bye. Thank you.